Hi everyone, my name is Amir Hussein, and in this video I want to talk about how we can use the spectral clustering algorithm in MeTa using the MeTTa-UL library. And here is the link to the GitHub repository. I recommend you clone the project, read the documentations and implementations, and start playing around with the code. So we are going to talk about MeTa and its key features. Then we quickly go over the spectral clustering algorithm. After that, we begin with how to install the MeTa-UL package and go over how to use it and apply the spectral clustering algorithm in MeTa using a simple dataset. Then we run the codes and we conclude the video. So MeTa is a programming language for computations over knowledge graphs, which are referred to as Atomspace in MeTa. Each program is a subgraph of this Atomspace where atoms, which are nodes and edges of this subgraph, represent symbols, expressions, variables, and grounded data. Symbols represent concepts, or identifiers. Expressions are schema-like constructs. For example, F and A are coupled here, or Socrates is human implies Socrates is mortal. Variables are denoted by $sign and are used for pattern matching in Atomspace, and grounded atoms are used to encapsulate data like numbers, neural networks, with custom execution logic. And if you're watching this video, you are probably familiar with MeTa, but I encourage you to check out their website at this link. There are a set of practical tutorials here that can help anyone get hands-on with MeTa as quickly as possible. So MeTa has certain features that makes it an interesting choice of language for implementations related to AGI, or artificial general intelligence. For instance, it is a multi-paradigm language that combines elements of functional, logical, and probabilistic programming. It is a framework for representing both declarative and procedural knowledge. It enables you to write the code that you can modify inside the program, and we will see an example of this functionality later in this video. It supports state-of-the-art type systems, and also MeTa enables us to write probabilistic logical reasoning routines, which makes it a good choice for neural symbolic reasoning programs. And it runs in a non-deterministic manner, which makes it an inference engine over knowledge graphs. So our goal in this video is to showcase an example of spectral clustering algorithm using MeTa library. But before we do that, it is good to have a review of the spectral clustering algorithm. So our input data is a set of endpoints, xi's, where each point is in RD, and the goal of the clustering algorithm is to partition this data set into k clusters. So the first step of the algorithm is to compute an affinity matrix where each entry is the similarity between the corresponding pair of data points. By default, we use a Gaussian kernel, or RBF, which stands for radial basis function kernel, to compute this similarity. The affinity matrix has the shape n by n, and its entries are computed as this formula here. We take the norm of the difference of two data points and pass the result to a Gaussian kernel with variance sigma. Then, based on the affinity matrix, which can be regarded as a fully connected weighted graph, we are going to compute its degree matrix, which is a diagonal matrix where the entries of each node is the sum of all incoming weights to that node. Then we compute the normalized graph Laplacian using the affinity and degree matrices. The next step is to find the eigenvectors and eigenvalues of the normalized graph Laplacian. we select the k first eigenvectors that correspond to the k smallest eigenvalues and refer to them as spectral embeddings. And then we are going to normalize the rows of spectral embeddings to have unit magnitude. And finally, we want to apply the k-means clustering algorithm to the normalized spectral embeddings to find the k clusters of data. So this is a basic implementation of clustering algorithm. Now the first step to use spectral clustering in MeTa is to use MeTa library in Python. This is done easily using Python's package manager pip by creating a virtual environment and running the pip install command. UL in MeTa-UL is short for unsupervised learning, and this package contains basic implementations of clustering algorithms such as k-means, Gaussian mixture models, spectral clustering, and hierarchical clustering that includes bisecting k-means and agglomerative clustering algorithms. After installing the MeTa-UL package, we are ready to write the script. I recommend reading the official MeTa tutorials to get familiar with the MeTa syntax and concepts. The first thing that we should do is to import the necessary modules of the MeTa-UL package using these 3 lines. MeTa-UL contains the main modules such as Python Meta integration tools that handle grounding the Python objects and functions. It contains wrappers for data science libraries such as NumPy, Pandas, and scikit-learn. It also has array and data utility functions and other implementations for other clustering algorithms. The second module contains implementations of basic spectral clustering algorithm. And finally, the helper module contains data transformation utilities specifically designed for processing Pandas data frame in MeTa. Next, we will import Python's data science packages and modules using the pyimport and pyfrom commands that are implemented in MeTa-UL based on its pyatom command. These commands mimic the import and from commands in Python and add the module or submodule of Python programming language in the Atomspace. For example, constants of packages are transformed into value atoms. Important functions become operator atoms, and classes are added as value atoms. And this allows us to use the functions of these packages in MeTa. After importing all necessary modules, we are going to read the CSV file of our dataset in MeTa. And we use the California housing prices dataset from Kaggle platform. The dataset has 10 features, including numerical and categorical data. You can check out the detailed characteristics of this dataset at this URL. We read the data using pandas read_CSV function, and we bind it to the variable df here. Next, we are going to store each row of the data frame as a separate atom in the Atomspace. This allows us to apply MeTa-specific operations over data rows, such as pattern matching in MeTa. We store the data rows as atoms using the import pandas data frame function that is implemented in the MeTa-UL package. This is a syntax where the first argument is a pandas data frame and the second argument is the name of the atoms. For example, calling this function results in these atoms: house index 1, feature 1 with value x1, and feature 2 with value x2, or house with index 2 has x3 as its first feature and x4 as its second feature. And same applies to other rows of the data frame. Now we need to transform all the data atoms into a single data matrix of NumPy array type for data processing. We begin by matching all the house atoms of this form and apply the df values function to their IDs and properties. The df values function, which is defined in the MeTa helper module, transforms a row to a simple flat expression of indices and values. For example, house 1 with feature 10 and feature 20 becomes 1, 20, 10. This converts the rows into simple expressions of values. And then we collapse all the values into a single expression and then transform them into a NumPy array. And finally, we bind this NumPy array to the variable data that we have here. Now that we have prepared the raw data matrix, we want to pre-process for spectral clustering. Here we have defined a pre-function that takes the data values as input, passes it through a sequence of pre-processing transformations, and returns the results. And we bind the pre-processed data to the variable x processed actually. We first exclude the first column of data that includes the indices of data points. Then we define a simple imputer object from scikit-learn, and we get the numerical and categorical features of house data. After that, we fill the NaN values of numerical columns with the corresponding features median using simple imputer. We also define a one-hot encoder for categorical values that encode them accordingly, and we concatenate numerical and categorical results into a single NumPy array. And finally, we standardize the data using scikit-learn's standard scaler. At this point, our data is ready to be clustered using the spectral clustering algorithm. There are two main functions to use the algorithm, namely fit and predict. The fit function implements the main algorithm and retains the clustering centers, while the predict function assigns the labels to the input data. And we define a wrapper function, fit-predict, here that calls fit and predict sequentially and returns the labels. You can view this spectral clustering.meta file in the repository to see the implementation details. Also for API reference and technical reports, view these MD files in the docs section of the repository. We also define a dimensionality reduction function that uses scikit-learn's Tisney algorithm to reduce the dimension to 2 for visualization purposes. Here we call the algorithm over process data and get the clustering labels. We then call the reduce dimension function on the process data to compute the x reduced data with dimension 2 for visualization purposes. And we visualize the data using the Seaborn Python package. We cluster labels to assign the colors of data points. Here we want to export the labels into the Atomspace by assigning cluster labels to each data point. We do that using the cons labels function, which takes 3 arguments, where the first argument is the data matrix, the second argument is the cluster labels, and the third argument is the name of the atom that maps data index to cluster labels. An example atom is cluster label with index 1 has cluster 0, which indicates that the data point with index 1 has the cluster 0. Up until now, we have shown the basic steps of a clustering pipeline in MeTa using the MeTTa-UL library. These steps include loading the data, pre-processing the data, fitting the clustering algorithm, and assigning the labels, and finally visualizing the results. Here we want to show the dynamic adaptability feature of MeTa that we mentioned at the beginning. Since every subprogram in MeTa is represented as atom, we can remove different functions and add new ones dynamically in the runtime by treating them as atoms and providing that the input and output types are consistent. Here we want to remove the compute affinity matrix function of a spectral clustering, which is based on RBF kernel, and replace it with a new compute affinity matrix function, which is based on the KNN binary similarity graph of data points. To this end, we first match the compute affinity matrix and then remove the match atom from the Atomspace using the MeTa's remove atom command. Once we remove the RBF based affinity matrix computation, here we define the new graph-based affinity matrix with the same types of inputs and outputs that are required by the algorithm. The new function operates as follows. First, it computes distances between all pairs of data points, and for each data point, it sorts the distances ascendingly. Then it creates the KNN graph adjacency matrix, and finally it returns the adjacency matrix of the KNN graph as the affinity matrix. Finally, we run the clustering algorithm again and show that the algorithm works fine with the new compute affinity matrix. So here we want to review the codes, run the codes on the IDE. So as you can see in the root path of the project, there's a Python file named run-examples.py, which is responsible for running the example scripts for spectral clustering. The examples themselves are placed in the examples folder, and their names are test spectral.meta and test spectral adaptive code change.meta. So first we are going to run the basic example of spectral clustering by running this run example script here. So after running the algorithm, you can see that the spectral clustering has clustered data points into 3 clusters, and here is the 2D visualization of our data point, which are reduced by Tisney algorithm. And so this is the basic implementation, and you can change the parameters of RBF kernel to fine-tune the performance of the algorithm to your desired output. And next we want to run the second example. So here we run it through the run examples.py, and in this example, as you can see, we are going to remove the default compute affinity matrix of spectral clustering and define a new one which is based on KNN similarity graph. Once the codes are executed, you can see the new clustering results. Again, we have defined 3 clusters for this run, but the difference is that here we have used the KNN binary graph as the affinity matrix, and as you can see, the results have changed, and this shows that the choice of affinity matrix is in clustering is very important, and it's a design choice that should be made by the engineers in order to find the best clustering results that they like. So in this video, we talked about the MeTa programming language and the spectral clustering algorithm. We showed how to use the MeTTa-UL library to run a clustering pipeline, including the data loading steps, pre-processing steps, and running the spectral clustering algorithm. And we also reduced the dimensionality of data for visualization purposes. And finally, we showed how you can use MeTa to change the code in runtime. And thank you all for watching this video. Again, I encourage you to clone the MeTTa-UL repository and start running the examples on your local machines. And you are welcome to contribute to this project. And I also recommend reading MeTa's official tutorials. If you have any questions, here are the email addresses of our team members. We are more than happy to hear from you. Thank you.